This is Professor Clements with another wave optics example regarding the double slit. We have a double slit here that is, the slits are separated by 0.0018 millimeters. These are close together. But it's possible to create a situation like this with today's technology and technology of 100 years ago. We're having light of 670 nanometers come into these slits, and the light is coherent such that we get a peak at the two openings at the same time, or get a valley at the two openings at the same time. So it's organized light, and we're interested, a screen 2.9 meters away, 670 nanometers for the wavelength, and someone says, calculate for me the distance from the central max, that's going to be right in front of the two slits, out to the third order maximum. What is the distance on the screen out to there? Well, in general, if this is L and someplace out here is Y, we would want to do tangent of theta equals Y over L. We are given L, we want to calculate Y, so we need to somehow come up with a value of the theta. We're trying to calculate a maximum, so we would use the equation d sine theta equals m lambda. D is the distance between the two slits, theta we're trying to calculate, m is the order number. So we're going to be using a 3, an integer 3 there. And the wavelength has been given 670 nanometers. Well, it seemed like we just have to plug in the values and see what result we come up with. So let's do that. Converting this first just to millimeters in scientific notation, I would have 1.8 times 10 to the minus 3 millimeters. You see you have to shift 3 decimal places to get the 1.8. And then I'm going to write it in meters. That 1.8, a milli is 10 to the minus 3, so 10 to the minus 6 meters. That's our value for D. The wavelength, 670 nanometers. I'm going to keep the 670. 10 to the minus 9 meters. Nano is 10 to the minus 9. So now we have the same units for D and for the wavelength, and we can legally do our calculation with the division that will have to take place, m lambda divided by d. So we'd have sine theta is m lambda over d, and putting in our values, we were told to find the third order maximum, so I use a 3 for the m. For the wavelength, 670 times 10 to the minus 9 meters. For the separation of the slits, 1.8 times 10 to the minus 6 meters. So you ought to pause and do your own calculation now. What do you get for the value of sine theta? I came up sine theta of 1.117. Oh, that's interesting. I hope it's interesting to you. So go ahead and use your calculator and find the value of theta. Of course, you have to take inverse sine of both sides. Inverse sine of sine cancels, these two functions cancel, we just have theta. And then you have to take inverse sine of 1.117. So how did that go for your calculator? You definitely should pause and try this on your calculator. I hope I didn't break your calculator. What's the difficulty here? Why is your calculator displaying an error message? It's because this 1.117 is out of the domain of the inverse sine function. This is illegal. This theta does not exist. This theta does not exist. The third order maximum does not exist. So if the order gets too high and your slit is a small separation, then this problem will occur. So that's something you need to keep in mind. Well, what about the other orders? M equal 1, the M equals 2. the first order. Is there a location on the screen for those? Let's just calculate the angles. So d sine theta equals m lambda for m equals 1. We'd have 1.8 times 10 to the minus 6 meters is our separation of the slits. Sine of theta, 1 times 670 times 10 to the minus 9 meters. You should run this through your calculator. Hopefully you have sine of theta of 0.37, then a lot of 2's. Taking inverse sine, I came up with 21.8 degrees. That first order does exist. I'm not going to bother to calculate where it is on the screen. Put this into the tangent calculation. Tangent theta equals y over L. And you can calculate the y. What about m equals 2? The only thing that changes is we're going to have a 2 instead of a 1 here. Well, that means the sine of theta is going to be 0.74444. The 0.74 here coming from doubling the 0.37 and doubling all the 2's, I get 4's here. If you want to do it a different way, rework this whole thing with a 2 here, run it through your calculator. This is what you'll come up with. The inverse sine now produces the angle, and I got 48.1 degrees. So this is the m equals 2 angle. Here's the m equal 1. Are these angles proportional? M has changed from 1 to 2. What if I double this angle? I went back to here and did a doubling and then took inverse sine. Yeah, it's another step on your calculator to take inverse sine. Why not just double the angle? The sine is not a linear function. The sine is not linear. So when m changes by a factor of 2, the angle does not change by a factor of 2. A factor of 2 here would be 43.6. Definitely not the case. And then I would not add another 21.8 degrees to this to find the m equals 3 location. M equals 3 location doesn't exist. So be careful on doing proportionalities. The sine is not a proportional linear proportional function. So you must go back and do the calculation with the inverse sine. So that's an example. Our original problem here, and the main point is that if m is too large with a small slit separation, you can run into these situations where the predicted angle does not exist. Impossible to find it. We cannot take the inverse sine of something bigger than 1. You can try lots of numbers in your calculator. Take inverse sine of 2, 3, 4, 5, 7, 23. All of them will show an error message on the screen. And after a while, you will believe that the inverse sine of something bigger than 1 does not exist. So keep practicing. Ask your instructor some questions.